Okay, this time let's see orthogonal spaces. To motivate this idea, I give you here 4 pictures. So let's analyze each one and see what conclusions can we take. Here we find 2 lines, the line U and the line V. They are clearly both subspaces of R2, because first of all they are lines, and second, they cross the origin. Additionally, they are orthogonal, which means that every vector on U is perpendicular to the vector V, the perpendicular meaning orthogonal. They make 90 degrees between both. As such, we can actually write R squared, the entire plane where these lines live, is equal to the direct product of U plus V. So any vector in this 2-dimensional space can be written as some U plus V. So R can be written as U plus V, some appropriate linear combination. So this is very important. A second important thing is to say that, well, U, or direct product with V, gives us the whole space, the R squared space. And thus, we say that V, for example, is the orthogonal complement of U. So V here is U perpendicular, the orthogonal complement of U. Because it's, if you start with U, the subspace, well, what is missing? What vectors are missing for me to reach the entire 2-dimensional space? Well, the answer is the orthogonal complement, in this case, V. Notice that if U and V did not make 90 degrees, make some other angle, well, I could still write that the R squared is U direct sum with V, fine, but I could not say that V is an orthogonal complement, because in this situation, the subspaces are not orthogonal. That's it. But you can still write R as some summation of U plus V. That is fine. Now, looking at our second picture here, I draw you 2 rectangles, which are supposed to represent 2 planes that intersect at the y-axis here. Are these are clearly subspaces of R squared, of R3. They are subspaces, they contain the origin, and they are closed under linear combinations. But are they orthogonal spaces? For them to be orthogonal spaces, it means that every vector on U must be perpendicular with any vector on V. But if you take, for example, this vector here, like that, this vector belongs to U, but also belongs to V. And it's not orthogonal. See, any vector on the y-axis belongs to both spaces, and they are not orthogonal in this situation. In this case, I could write R cubed is equal to U plus V. I could also always write any vector in 3-dimensional space as some summation of U plus V. But they are not orthogonal to each other, these 2 vectors. And moreover, there is no orthogonal complement in this situation as well. Now, the third example here, well, I have here the plane V and U. Again, the U here, vertical axis. Is it true or is it false that any vector in V that lies along the V plane is always perpendicular to any vector on U? Is it true or is it false? It's true, right? Every single vector makes 90 degrees. It is the angle. Any vector that lies on this plane is perpendicular. So I can write again that R3 is equal to U plus V, and moreover I can say that V is U perpendicular, meaning the orthogonal complement of U, because it's just enough. It's just exactly what you need. is what you need to reach every point on R cubed. If you start with the vertical axis, well, you need to complement that with a plane, and vice versa. So V is orthogonal complement of U, and U is orthogonal complement of V. Now, on this fourth example, I have here two lines, essentially living on the y plane here. Again, in this case, it's not the case. It's not the case that R3 is U plus V. This is false. Because I can never write a vector, for example, I can never write this vector as some combination of the green and pink vector. Never. Because by combining those two vectors, I'll always live on the xy plane. I never leave that. So this is not true. However, what I can say is that the xy plane, that indeed is equal to the direct sum of U plus V. That's true. This is true. But not R3. It's not enough. Moreover, they are orthogonal complements with respect to the xy plane. See? When you talk the complements, you need to talk about the whole thing. What's missing from V to get to the whole thing, or what's missing on U to get the whole thing? Well, it's the orthogonal complement. If that subspace is orthogonal to the one you start with. Well, all these examples essentially motivates us for this very important definition. U being orthogonal to V means is the same thing as every vector U is orthogonal to every vector in V. And orthogonal means the dot product is 0. That's it. Orthogonal complement of U with respect to Rn. Again, Rn is the whole thing. What's missing on the subspace U to get to every other place? And by the way, what's missing, and it is in turn orthogonal to it? Well, we have a name for it, is U orthogonal, and by definition is all vectors from Rn, all Vig vectors from Rn, which have this property, which is the property of being perpendicular to every vector U of U, right? Read this carefully. For every U in U, I want the inner product of that U with the V to be 0. So this is the element U test. The test that every V must have. For example, if I choose here, very easy, if I choose here the U, right? The orthogonal complement, as we have seen, is V, right? That means that every vector V obeys this property, which means every vector U, when dotted with V along this line, the green line, is 0. That's what this thing means. Just a very short annotation for describing what our intuition was telling us in those pictures. Finally, let's just read this note. Orthogonal complement of U in Rn is a subspace that complements U to gives us Rn. It's what I've been saying, what's missing. And it is the solution. It is a solution. The solution is named U perpendicular of this equation. So notice, this is an equation. Rn is U direct sum with U perpendicular. I want to solve this thing. Rn is given, U is given. What's U perpendicular? Well, the answer is the solution set. The solution set of this equation is given by that. You need to compute that. The elements of the set, you have to compute those. Moreover, if the dimension of the whole space is, the dimension is n, and the dimension U is some number, could be m, of course, n minus m is the dimension of U perpendicular. So again, the summation of both spaces is n, as is expected. The summation of the dimension of U, the dimension of V, is 2, dimension 1, dimension 1. In this case, dimension 2 for the plane, dimension 1 for the line, By the way, with the dimension, let me recall it. The dimension is the number of basis vectors that you need to span V on U. For V, you need two vectors because it is a plane. For U, you just need one vector. So dimension 1, dimension 2, the summation is 3. Well, but that's R3, the dimension of R3. Here, the same thing. The dimension of the green subspace and the pink subspace, summing just gives 2, but the whole thing is 3. So no surprise that R3 is not a direct sum of both. That's it. Very important ideas, and we're going to explore this idea further in next videos. Finally, let's see one more application of our inner product, the new concept that we have been introducing. In this case are the 4 subspaces which can be computed from a given matrix A. You find here a matrix that we already have seen many times during this course, and for which we used the elimination steps to make it as simple as possible, like so. We've seen that we have a pivot here and a pivot here and 2 dependent columns. From that form of the matrix, the row-reduced echelon form of the matrix here, we were able, like we did in previous videos, to compute the column space. The column space here of the matrix A here, well, are the independent columns. In this case, the first and third column, because after simplification, that's where the pivots are going to land here. Also, we computed in previous videos the nullspace of A, the solutions. The solutions of AX is equal to 0. And the solutions, well, looking for the dependent columns, we tried to annihilate them by combining them with the independent columns here. In this case, if I multiply this column by -2 and combine it with this column, well, I get 0. This is exactly what you find here. The coefficient of the first column, the coefficient of the second column, and all the others. Let's remember again, if I choose this column, meaning 1 here, the coefficient is 1, what coefficients x and z must be so that to make this 0? Well, you have to have 2 of these, because 2 of these makes 0 with that, and you have to have -2 of these, because -2 of this plus 2 of that, well, gives 0. Can you see? This is what the coefficient that you find here. Of course, this column is multiplied by 0 because it's not needed during the process of computing the nullspace of A. Now, this is nothing new. This is a recap. What's new here, well, is there are 2 more spaces. The column space of the A transpose and the nullspace of A transpose. And this is what we want to compute now. The 2 missing things that we need to have a complete picture of the matrix and how it operates. So let's see. Now, row space and left nullspace. The column space, meaning, in other words, the column space of A transpose and the nullspace of A transpose. Here is the transpose of the previous matrix. After elimination steps, we find here 2 independent columns, 2 pivots here, and 1 dependent column. In this form, the reduced row echelon form, we can now easily compute the column space of the row space of AT. Well, what's the row space? Well, looking at this column and this column, they are the independent. Therefore, this column and this column must correspond to the columns that I need to span the column space of A transpose. They are the independent ones. Only need those. So this is what I put here. The first and second columns here. So there is nothing new. And the same way that we compute the column space of A is the same strategy that we use to compute the column space of A transpose. So that's it. You just do the calculation again, but instead the elimination steps, but you do it with the A transpose. Now, there is also something else we can compute with this, because we have a dependent column. Therefore, what are the coefficients of the first and second column that annihilates this column? Well, if I choose the coefficient 1 for this column, this one here, only need -1 and -1, right? The -1 this column makes this 0, -1 this column gives this 0. So the nullspace is the span of the entire thing. All the linear combinations, multiply this vector by any constant. So essentially there is this idea that you first compute the column space and null space from A, and then you do the same thing with the transpose. And you have these 4 beautiful sets, these subspaces, that are going to be very important in the future. But now let's see one of their first properties. Well, one of the first properties that we can derive for these 4 spaces for the matrix A is as follows. What you find here, well, this is what we just computed in previous section. But below you find here the matrix A, here, the original one. In yellow you find the rows, the 3 rows. Here you find a vector multiplying this matrix, giving us 0, 3 zeros, 1 for each equation. So essentially the solution set of this system of equations is the null space of A, like we have computed in previous videos. And whose solution, by the way, is the span of these 2 columns. So quite easy, we already seen this result. But notice about the calculation. Notice this calculation. Any vector in this span, when I put here, multiply by this matrix A, gives us 0. Which means that when I choose any vector that I have here, I put here, make the dot product with the first equation, gives a 0. When I choose any vector, put here, multiply by the second, gives 0. And again, by the third, gives a 0, right? Can you see it? Any vector that I choose from the null space of A, when I put here, dot with the first row, second and third row, gives a 0. But remember what is the first and second rows. The first and second rows are the vectors, are the basis vectors for the row space. Think about it. What this means? It means that every vector in the null space must be orthogonal to any vector in the row space. Can you see? In fact, you can check this. Just choose this vector and this vector. Are they orthogonal? Let's do the dot product. Multiply the entries. So 1 here times -2 plus the second entry 2 times 1 plus 2 times 0 plus 2 here times 0 here. What calculation gives us this? -2 plus 2 is 0, right? This is 0. So it's orthogonal. You can do this with the other combinations. And you can check that this basis is orthogonal to each other. But that's true. It's true for any linear combination. Which means, in fact, that the column space of a transpose is the orthogonal complement of null space of A. It's very important. I want you to think about it. Because look at the vectors. The vectors have 4 entries, so they live in R4. These are 4 entries, so it also lives in R4. This has 2 dimensions, this has 2 dimensions. They are orthogonal. Which means they must be orthogonal complements, right? They are orthogonal complements. The dimension of the row space for the null space is 4. Just like R4 where these vectors live. So this is the first key idea. The second key idea is not very different. You already anticipate. How did we compute the left null space, the null space of a transpose? Well, we solve this problem. We have a transpose, the 4 rows, the vector here with the unknowns, and the solution of this system of equations is what we called the span of -1, -1, 1. So any vector that I choose along this line, I put here, I dot with the first row, gives a 0, with the second row gives a 0, and so on. So any vector in the left null space, or the null space of a transpose, must be orthogonal to every vector in the column space of A. Very important idea, just like we've seen here on the left hand side. Moreover, these vectors have 3 entries, so they live in R3. this subspace has dimension 2, this has dimension 1. So the column space is the orthogonal complement of the left nullspace, and vice versa. Can you see? The column space is the orthogonal complement of the left nullspace, and the nullspace is orthogonal complement of the column space. And finally, now that we have these four spaces and we arrive at the conclusion that this is our orthogonal complements, they complement each other in R4, this on R3, let's make a picture out of it. Finally, here's a picture for our four spaces that you find here. Very easy to see. So the column space here with two dimensions that you find here, well, is this rectangle that you find. 2 dimensions, rectangle. The left nullspace, just 1 dimension, is this line, represented by this line. Every vector on the green on the column space is perpendicular to the vertical line. Can you see the idea? Here on the left hand side, you see the nullspace in blue. Again, 2-dimensional. With this basis. And the rowspace of A, or the column space of A transpose, again 2-dimensional, 2 vectors. So what can we conclude? What can we conclude? We already have seen that these two are orthogonal complements and gives us R4, exactly where these vectors with 4 entries. On the other hand, these live on R3. So R3 has 2 subspaces, column space of A and the left nullspace. The R4 also has two subspaces, these two. Which means, because I can write R4 as the direct sum of both, and R3 as the direct sum of these two, I can write any vector. For example, this vector x must be some combination of a vector living in the row space and in the null space, just like you see here. So x must be x row plus x null space. Here the same thing. In green, the vector, let's call it b, well, must be some part living in the column space, b, let's call it bc, of the column space, plus b left null space. Can you see the idea? So vectors living in R3 can be decomposed like this, and vectors in R4 can be decomposed like that. Very important idea, because it will play a key role when we try to understand whether a system of equations has 1, 0, or infinite solutions. So this is a picture that you need.